So we introduced the work energy theorem last chapter, and we got through the majority of that chapter. I showed you how to take a force. We described the conservative and non-conservative forces, just as a quick review. A conservative force, quick and dirty method, any force that can cause something to accelerate without touching it, or without the elements or the origins of the force touching. The only two forces, well, really the only force that we've discussed that is that kind of force is gravity. Gravity doesn't need to touch a mass in order to accelerate it. Whereas all of the contact forces that we've discussed, friction, normal force, drag force, they require contact. And in doing so, mechanical energy will be converted to heat. When you rub your hands together, it's the contact and the friction between the hands that causes a chain that does work essentially at the surface. Contact and converts that mechanical energy of motion, into heat energy. Now, heat is a kind of energy, but it's just not mechanical energy. It's heat. It is its own classification. Heat is the physics, the correct physical name for the kind of energy that is associated with heat. It's kind of a redundant name in a sense because it's become such a part of our psyche that we don't separate heat from the name, right? Like we do with other things. For example, potential energy is energy of motion, of position. So that concept is kind of separate from the stuff that is converting from work to potential to kinetic energy. Whereas with heat, we just think of it as heat, but it's still the same energy as the stuff that's associated with mechanical or kinetic or any other kind of energy, but it comes through in the form of heat. So just to make that distinction for you. And yeah, we defined work. We showed, we derived kinetic energy and showed the relationship between work and kinetic energy. It's called the work energy theorem. And we know that work is equal to the change in kinetic energy. And I also took a gravitational force and put it in the definition of work, the general definition of work, which is this integral here, F dot dx or dr in general. And so we take the gravitational force, mg, put it in there. And from that, we derived the gravitational potential energy, which has the formula mg times delta y or delta whatever, so whatever the position is. And late, in high school, we would call the delta YH, so MGH, that's where that formula comes from. But in the process of deriving that, we showed that there's actually a relationship between potential energy and work. And because work, you can do positive and negative work. Positive work means energy goes into the system. Negative work means energy comes out of the system. We have to throw in a negative sign when we throw in that relationship. Kinetic energy is a scalar. Potential energy is a scalar as well, but it's a function. And because it's a function, which has this delta y, you can traverse the delta y in a positive direction or negative direction once you define your axis. So even though it's a scalar quantity, you can have positive and negative work, a positive and negative potential energy. And what it means is not so much a direction, but as I said, energy going into the system versus energy coming out. Kinetic energy will never be positive, will never be negative. It will always be positive, just like a normal scalar. Anyway, when you do that relationship, you see that work is equal to the negative of the change in potential energy. Now, I'm going to say this is in general. I'm not going to put a G here because I just showed you this relationship with gravitational potential energy. But potential energy, any kind of conservative force has the potential energy. Gravity, magnetic force, and as we'll see in an ideal case, a spring force although it doesn't have, well, yeah, spring force. So this is a more general relationship. This is the general definition of potential energy. This is work energy theorem. This is the definition of work. And this guy is the gravitational definition of gravitational potential energy. Okay. So I definitely encourage you to make sure you know the names of these concepts mathematically and their mathematical representations as I've shown them here. Yeah, so we did that last week. What I would like to do for you now to finish up this chapter is I'm going to introduce a special force here, the Hooke's law force, which we associate with any kind of elastic force, rubber band, spring. And I apologize, I don't have any of that here with me in my little gadgets that I've been collecting. In my home projects, I had a rubber band, but I think it popped and I forgot to replace it. Check something. Yeah, so I don't have any rubber bands in the house anymore.
Professor,
Yes,
in the third equation, the words written after it is gravitational PE.
potential energy.
Okay, thank
Yeah,
you.
sorry. Yeah, they're abbreviated. Usually, kinetic energy and potential energy are abbreviated in the following way: KE, or kinetic energy. Now, sometimes also you just see K because people don't want to use the ink to write K, the periods and everything. And the same thing for potential energy. So yeah, um, I usually just use, once I introduce it, I usually just use K and P. So sometimes you also see P, just P, but also I because you can get that confused with other things later on, and I usually use K and U, U for potential energy. But these are all valid symbols. PEKE, My favorite are uh, K and U. Also, I mentioned it the other day, but I don't think I wrote it down. And I've been mentioning it the whole time. Mechanical energy, that's a thing. It's not just an adjective, it's actually a proper name. Mechanical energy is defined as the sum of kinetic and potential of any system. So it's basically the E is the total mechanical energy of a system, which is defined to be the kinetic plus the potential. And so the capital symbol E is the symbol for mechanical energy. And again, that's a specification, a distinction. So mechanical energy is different from heat, is different from uh, thermal uh, thermal energy, is different from radiation energy associated with radiation, which is yeah, yeah. So different types of energies. So I'm going to do a couple things here to finish out this chapter and then segue into the next chapter. And by the way, as I told you in my notes, these two chapters, which I think are chapters 7 and 8, they're just one chapter in my notes. So a lot of these concepts, like potential energy and stuff, they don't actually introduce them to the next chapter, but I've already started to introduce them in the way that I set this up. So I'm gonna do exactly what I did for you for potential energy. I think I asked you to do it maybe at home and read the book, but I'm gonna do it for Hooke's law. Hooke's law is the name of the force associated with any kind of elastic um, band or force. It's elastic force. It's the law that describes elasticity. And as you know from your personal experience, usually with something that's elastic, whether it's a rubber band or a spring, or even something like a rubber ball that you press it, the more you press, the harder it presses back. You know, the third law of force increases. Or stretching, same thing. The more you stretch a spring, the larger the force. And so what you find within a certain range of disturbance from the equilibrium of that system, it's a linear relationship. The force is proportional to the amount in which you stretch the object. And that's basically Hooke's law, that for an elastic force, F is proportional to delta X. And the proportionality constant, K, which is referred to as the coefficient of elasticity, right? Yeah, is the coefficient of elasticity is the proportionality constant. So that when you put those things together, you get that. Now, sometimes you for the Hooke's law specific, you can abbreviate with a K or sometimes with an H. People, you see that. I usually do it with either. I kind of go back and forth. But Hooke's law for Robert Hooke is it's a minus K delta X. Now this minus sign, even though this is a vector equation, this minus sign is not really about direction in the way that we normally think of it. This is a symbol that represents the fact that Hooke's law is a restoring force. A restoring force. I might have said this, I think I'm having deja vu right now. I don't remember if I said this to you or if I said it to my summer class. Is that what I'm remembering? But I said it to you before, it's worth saying again. Restoring force. So it's not a direction in absolute terms. What do I mean by that? Let's assume that we have a horizontal oscillator, that is a spring attached to a mass that's also attached to the wall, and we're at an equilibrium position here. And we stretch, we pull the mass away from the equilibrium position so that we stretch the string out and the mass is going to be over here somewhere later. Right. Okay, so this represents my stretched spring. Okay, so I've just taken this mass and pulled it away from the equilibrium position. Now, as I do this, so right now, this Hooke's law force is 0. Why? Because the delta x is 0, right? X minus x naught minus x naught is 0. Now here, if I stretch it out to x, then remember delta x by definition is x final minus x initial, so it's going to be x minus x naught. If you assume that x naught is 0, then delta x is just x. But my point is that once I begin to stretch it, the force begins to increase. It's kind of like our friction, right? I told you that when I was pulling on the object, remember we did that? I pulled on the object, and the more I pulled up to a certain point, the larger the frictional force got, right? When we were defining, when we were describing and defining the static frictional force. Right now, the frictional force is 0. Once I start to pull on it, even though the object is not moving, that frictional force has to pop out in the opposite direction and gets larger up to a critical point to the moves. Now, it's a different system, whatever, and different things, a different concept, but I'm just saying mathematically analogous, we see that with the restoring force. There's no restoring force right now. Once I start to pull that mass, the restoring force pops up in the opposite direction of motion and increases as I pull it because it's proportional to delta x. And by the way, the coefficient of elasticity is the larger it is, the stiffer the spring. So that's based on what your intuition might think, how it is defined. Yeah, it is defined that way. So what you see then when I'm out here is that there's a force on the object and it's pointing back toward the equilibrium position, trying to restore it back to that point. Hence the name, restoring force. Okay, delta x. Usually I just deal with magnitudes, and most books do when they're dealing with a restoring force like that, because, like I said, if I define my axis here, which I didn't formally, but I could, then that direction is positive and this direction is negative. And so it gets a little confusing if you try to speak about the restoring force in terms of its vector nature. And again, this minus sign has nothing, because it doesn't even know what you're calling positive and negative as when you define it. So clearly that's not really about the direction of the absolute direction of the restoring force. Really about the relative direction, the direction relative to the equilibrium position. So when I pull it out, restoring force is in that direction. Now, when I let it go, this restoring force will cause acceleration. The acceleration. Now, don't confuse acceleration and velocity. The velocity will continue to increase, but just like gravity, when I let this go, the maximum acceleration is going to be dependent upon the maximum displacement. As soon as I let it go, the acceleration starts to decrease as the velocity increases. So the acceleration is not constant for this type of situation. Acceleration decreases, and at the equilibrium position, the acceleration is zero and the velocity is a maximum. And we're assuming this is a frictionless surface, so once I do work and pull this object out, that energy will stay in the system forever because there's nothing to dissipate it. As I said, acceleration decreases, velocity increases. At the equilibrium position, velocity is minimum, velocity is a maximum, acceleration is a minimum at zero. And then because it has momentum, thing moves through the equilibrium position, and then the restoring force flips direction. Now points back in the positive direction and gets larger as the mass moves away from the equilibrium position. It is a maximum when it's the same absolute distance on the other side of the equilibrium position. So over here then, the frictional force, basically when I'm at negative x, let's say, the object will be here, and the restoring force, again, dealing with just the magnitude, will be the same magnitude, but in the opposite direction. And so that denotes half a cycle. I pull it out, start from here, go through 1/4 cycle, and remember at this point, and this is a property of this type of thing. Uh, and we'll talk about this more several chapters later when we get the oscillations, but just to drop a seed. The maximum acceleration is here, and the minimum velocity is at the amplitude, and the minimum velocity is zero. A quarter or at the equilibrium point, it flips. The velocity is maximum, the acceleration is minimal. Then in the second quarter, we're back at the amplitude again, and we have a maximum acceleration and zero velocity. Now go through a third quarter cycle, going back to this in the opposite direction, back at equilibrium, zero acceleration, maximum velocity, and then flips, and then the force goes to zero. Then the force flips and increases back to one cycle. And up and back is one cycle of motion, one period. And then it just starts over again. It keeps doing that as long as no energy is being dissipated. And that is an example of what we will call simple harmonic motion, which we'll talk about in the chapters of oscillation. So this is one really nice example of that scenario. Another way that we have with that is with simple pendulums. Right. And we'll talk about this next chapter, in chapter 8, because once even though we want to derive equations of motion for this, we can still figure out like what the velocities and things are because we can use conservation of energy, which I will derive before the end of class using equation 1 and equation 4. So these are nice problems that we can apply conservation of energy to. Spring problems, pendulum problems. And it's a way of determining certain kinematic quantities without having to derive the equations of motion. Now, with these types of problems, we will derive the equations of motion again in chapter, whatever it is, 12 or 13 with oscillations, but they require some specific mathematics and things that are a little bit different from what we did with kinematics in the chapters 2 and the first few chapters. So, yeah. So that's an introduction of Hooke's law. That's what it is. It's the restoring force, and we're going to now show for an ideal system that is we can assume that it's a conservative force for an ideal Hooke's law. Now, it's very it's a this is a huge kind of simplification. because I just spent a lot of time last week describing the idea of a conservative force, and I told you that a conservative force is always, well, I didn't say always because I was anticipating this, but is usually associated with a conservative field, i.e., gravitational field, magnetic field. And honestly, those are the only fields that I know of. Although, and you put them together, you have an electromagnetic wave, which is a kind of field. It's an oscillating field, actually. And as far as conventional physics, those are the only fields that have been described, and they're fundamental fields. They go back to the Big Bang. However, and just as a quick side note, I actually think there might, at least mathematically, I don't know if we can ultimately experiment is the best test, but I think it might be possible to describe another kind of field, one which we don't really think of as a field. And I call it a temporal field, stuff I'm working on. And if so, possibly that could be a conservative field that has a conservative force associated with it. But I digress. Outside of gravity, electromagnetic, and electrostatic, magnetostatic, those are the only conservative fields. And so the forces associated with them are the conservative forces that we normally deal with when we're talking about pragmatic. Now, what was the term I used? Practical or pragmatic forces that we are dealing with when I was describing centripetal motion to you. Told you that centripetal motion will never be one of the practical forces that we usually deal with. So it's practical forces I'm talking about. And so of those forces, there's only 3 that are conservative, and the others are all contact forces or various forms of contact forces. Now, with the exception of this guy, this technically there is contact, right? Because right here, whenever when you have when you attach the spring to the mass, there's got to be some contact somewhere. But what we say is that the cross-sectional area of the contact between the spring and the object is so small compared to the overall cross-sectional area of the object, I guess the spring as well, then whatever friction you have is minimal, and the heat generated from that is minimal, so it doesn't really take much energy out. In the ideal case, we say it takes none out. There's another thing, though, associated with an ideal spring. A spring has mass, and like just if any of you, maybe you were kind of high school geeks and you'd had sets, electrical engineering sets from like Radio Shack, or just maybe you play with wires, or I don't know, your experience, that if you just take a small gauge wire and you try to wring it and break it, because you can do that very easily, if you touch the ends, it'll sting you because it's gotten so hot just in probably turning it 10 or 12 times. You ring it around and pop it off. If you put your fingers on the end, it'll actually, well, it won't burn you. It'll feel like it's stinging because it's so small a cross-section area that the heat that probably would burn you if it were larger, it feels like a sting. And that's really interesting. So it's showing you that those atoms and molecules, remember the Einstein model. You think about all those things are rubbing together as you break apart that metal. And so it's just conventional friction. You can describe it in that way, in conventional sense. And so I guess what I'm trying to say is the spring itself, just by oscillating back and forth or stretching, will generate heat. And that heat is energy. It's got to come from someplace. So it will be coming from the fact that the spring is moving. So what we say to avoid having to think about that or account for that is that an ideal spring is a massless spring, because if it doesn't have any mass, there's no atoms or molecules to rub together, even as it moves. So an ideal spring, for those reasons, allow us to consider the spring as an ideal conservative force without having a field associated with it. So there's no conservative field associated with a spring, obviously. You might be able to mathematically define it in some way. It's possible. Maybe defining, you probably could, but there's not, we don't do that. And there certainly is no real field, I think, which actually begs the question, is there any such thing as a real field? I'm not sure there is, because you only know if it's there if you have something like a mass there and it has a force on it. But again, that's a more of a mathematical discussion, philosophical maybe even, but certainly mathematical discussion, which I don't want to have here. We just assume that this is a special case where there is no conservative field associated with that spring. So we say that an ideal spring then has a zero mass, rest mass or mass. And um, yes, I'll say here, m equals 0 and no field associated with it. And but it's still considered conservative. Conservative force. And finally, I'll say, give a little bit of a tribute to this guy. This guy's name was Robert Hooke. You look him up. He happened to be, if you can believe it or not, Isaac Newton's nemesis. Not that Isaac Newton saw him as a nemesis. It was the other way around. I think I've mentioned this before, but I'm going to mention it again here. This story is told in a really nice dramatization, the story between uh, Robert Hooke and Isaac Newton in the show The Cosmos, that one that I think I mentioned earlier, where science conquers fear, for the first season of Cosmos with Neil deGrasse Tyson. So I'm just going to abbreviate his name, Neil deGrasse Tyson. And the specific show is when science conquered fear. And it is episode season 1, episode 3. And it tells the story of Isaac Newton as a young man, gives a kind of a biographical. But he, had issues when he was a kid, abandoned by his parents, kind of screwed him up a little bit. His father died and his family or divorced, I don't know, something. And but he's a genius, goes to school, graduates from college when he's like 2, no, sorry, just probably 18. And starts teaching at Cambridge as a professor and was kind of a hermit. And Robert Hooke, who was the head, Robert Hooke was much older, like Newton was in his 20s, Robert Hooke was probably like in his 60s, 50s or 60s, and old guy. And he was the head of the Royal Academy of Science at the time. He was a contemporary with Halley as of Halley's Comet. So Robert Hooke and I forget Halley's first name, they were all trying to figure out, basically they didn't know it, they were trying to figure out gravity. But what they were called is just, they were trying to figure out the trajectory, what type of path, the functional form of the path of Halley's Comet, as it, went along its path. And it was during a time, this time, get what, when the Halley's Comet was visible in the sky, like late 1600s or 15, whatever it was. Anyway, Haley, remember there was this young, promising, brilliant scientist who had just started teaching at Cambridge. So, and Haley and um, Robert Hooke, they would meet with other scientists, at a coffee shop or someplace like this, like on a regular basis, trying to, you know, debating this thing, Haley's Comet. And Haley remembered that there was this young, brilliant dude, Newton, who had just started teaching, and thought he'd go and meet him, have a meeting with him, and ask him if he wanted to join the group. So he goes to him, and Isaac says, "Well, no, I don't really want to join your group, but I've actually figured that problem out already." And eventually, to make a long story short, he sent it to Haley, and Haley happened to have a publishing company. So he made a living. Interesting, not as a physicist or as an astronomer. And he just was blown away. Basically, it was the notes of what ultimately became the Principia. And not only had Isaac Newton shown, that universal law of gravity and that it was elliptical, he proved it theoretically, and along with the laws of motion. And so basically, I wouldn't say that Haley became a mentor because Isaac Newton didn't need a mentor, but he basically became a friend and he encouraged him to publish his work, which Haley did it. It was the first publishing of the Principia was through Haley's press that he had. Anyway, I've made this much longer than I really want to talk about it. But the point is that Robert Hooke was a kind of a bitter old dude, and he was jealous of Isaac Newton because Isaac Newton was a genius. And honestly, Robert Hooke was brilliant in his own right. He was one of the first people that made detailed copies of the moon's surface. And again, he just because the big technology at that time was telescopes. This was the late 1500s, so the telescope was like the iPhone of that day, I guess. And so people were using it to just do all kinds of stuff. And one of the things that Robert Hooke did was to look at the moon and then draw the surface, and he was really good at it. So you can look up and see some of his drawings. But they're pretty accurate, the part that he could see relative to what we have now. It's pretty much, and he was the first person to name some of those craters and things. Um, anyway, he was kind of a nasty old man, and he was jealous and insecure, even though he was brilliant. And he basically started bullying, if you can believe this, bullying Isaac Newton when Haley, went to it. And um, yeah, and they became like this huge rivalry, although mostly facilitated by Robert Hooke. I mean, Isaac Newton didn't need to be a rival to anyone because he's the smartest person in the world, and he knew it. So, uh, yeah, but it's probably worth it. Take a look at that if you can find this free somewhere. It's worth. It's really interesting. They have these really nice animated cartoons that dramatize the story, and it's really, really good. So, yeah, yeah. That's introduction of Hooke's law. So let's take Hooke's law and throw it into this function over here and derive the potential energy function for a spring. Remember, it does not have a field, but because there is a force, we can use it to derive a potential energy function. So let's do this case. I'm going to calculate the work done now it's not the work done by me, it's the work done by the force as I pull this thing from equilibrium out to positive x. So I have to work out this equation. Work is equal to the integral from x naught to x of um, f dot fh dot delta x. The first thing I'm going to do is work out the dot product. So fh delta x cosine of theta. The theta is 180 degrees, right? Because delta x is, in that direction, and restoring force, as I told you, in that direction. So 180. That generates a -1, which I'm going to take out of the integral. Also, I'll go ahead and put in kx. Now, again, just like we've seen this before, don't let this confuse you when you're doing the integral as a math like it did me. You work out the dot product first, and you see there's a negative sign. But this negative sign that's generated from this dot product, that's the same negative sign that's in the definition. So you don't want to then put it in again once you put in the value of kx, because then you'll introduce an error. It's the same negative sign. So that's why, again, another reason why I just like dealing with the absolute value of kx as opposed to kx usually. So I will have a minus integral x naught to x of kx. And the other thing is you can think about is just that another way to get to that is if you actually use the definition of oh, sorry, this should have been dx. Sorry. For an integral, the delta x goes to dx. It's just the definition of the dot product. That's another way to think about it. So k x dx, and the minus sign is there. So yeah, that's it. And so k comes out of the integral. So minus k integral, basically from 0 to x, or x naught to x, of x dx. Drop my numbering, so 11, 12, 13. Okay. So the work then will be equal to negative k. And when I integrate, x dx integrates to 1/2 x squared from x naught to x. So that just gives me that this guy is, the work is equal to minus k. Now, I could make that 0 or whatever. It's just, but in the end, it's going to be negative k, 1/2 k delta x quantity squared. What we say. Now, if you actually did the work done as it, when I let it go and it goes back, it's going to be positive work because the units flip. I mean, the integrand and stuff is still the same. You're going to have a negative sign generated because f is in the negative direction and k is still in that direction, but it generates another negative sign because now the units flip. This is the 0 is final and x is initial. So you would generate a minus sign out of that, and the work will be positive. And in that case, the energy is not really coming out of the system. The positive means that it's not putting energy into the system. What it's doing is converting the potential energy, the 1/2 k delta x squared, to kinetic energy here at the equilibrium point. Because the potential energy obviously will be 0 here because delta x is 0 here. But the energy hasn't gone out of the system, as I told you, because we don't have friction here, so there's no heat being generated. So what did the uh, restoring force do? What type of work did it do? How is it positive if no energy is going into the system when it goes from the amplitude x to x naught? Well, it's the restoring force. The work has converted that potential energy into kinetic, where the kinetic energy would be 1/2 mv squared at this point, and that total 1/2 mv squared is going to be equal to all the potential energy back at this point, the 1/2 kx squared. And we'll do a problem where we illustrate that. But that's really an example of a practical application of conservation of energy. Well, we'll get to that a little bit later in class today. So yeah, so I guess the point I'm trying to make is that when I'm going from x naught to x, I get negative energy. But when I go from um, so this is work done when I go from x naught to x equals a negative 1/2 k delta x squared. When I go from x to x naught, I'm going to get a positive 1/2 k delta x squared. And we see that kind of thing with gravity when we did before. When I pick up an object from the ground, gravity does negative work. But when I let it go and it drops down, gravity is doing positive work because, again, it's converting that potential energy, that mg delta y, into 1/2 kx squared. So we see like an analogy, mathematical analogy between these systems, even though they're very different forces and they're very different potential energy functions that describe them. So again, symmetry, that's a symmetry, a mathematical symmetry between these types of systems that you want to pay attention to. But also the point I want to make is that because every quarter cycle, you're going to get negative work done, right? Because that's one cycle, come back in a half cycle. The third cycle, again, negative work is being done because the delta x is in the opposite direction of the k. And by the way, there'll be 3 negative signs generated there. And so still 3 negatives will still give you a negative. But I won't do that. I'll let you work that out if you want to. But so when we realize that this is a function, this 1/2 kx squared, when we define it and define the relationship that it has with work, we have to put in a negative sign in the definition because every third cycle you're going to get a negative sign for the work. So what we say is that the potential energy for Hooke's law is defined as 3 equal signs, is defined as 1/2 k delta x squared. So we define that quantity as a potential energy. But then when we relate the potential energy to work, well, first of all, we realize it's always got to be a change in potential energy. It doesn't really make sense to talk about potential energy at a point, as I've said before. It's really about the change in potential energy that really affects us. So, but when we define that change in the relationship to work, we have to define it with a negative sign because of that negative sign that comes out every now and then whenever we're calculating that work. So negative of the change in potential energy. So again, we're back to the general definition of potential energy. And this is why we have that. So put H here. Well, it's just that in general, but specific for this, the relationship would be for this type of potential energy would be UH. Okay, cool. So that's it. That's it. I need to take a quick break here, just a few minutes. When I come back, now that we've derived 2 potential energy functions, it's time to derive, in general, to derive conservation of energy, which we can do in a couple steps. As I said, I've erased the equations here, but using basically the work energy theorem and the general definition of kinetic energy, of potential energy, if two things are equal to a third, they must be equal to themselves, to one another. And we can use that idea to, within 3 steps, derive conservation of energy. So let me take a quick break, and then I'll come back and we'll do that, and then we'll apply it to those two problems, actually, the one dropping an object from height h and allowing a spring to restore something to its equilibrium position, and show you how to utilize conservation of energy. Right back. Okay. What am I doing? I just finished writing that. So yeah, I guess we're gonna do the problems, or was there something else? I finished the derivation, right? Yeah, I guess I'm just gonna apply it to these problems. Since I'm doing this, let's just go ahead and do that one. Oh no, yeah, I have to derive conservation of energy. Yeah, so I want to keep that picture there. So I'm gonna keep this here. It's only gonna take a couple steps. But to get the first form, but then we need to change it around for all the different forms. Yeah, I like to do and show you the best form, the most practical form for applying conservation of energy to problems. So again, I'll write down those two equations that I erased. The general definition of potential energy is that work is equal to the negative of the change in potential energy. And the work energy theorem is that work is equal to the change in kinetic energy. Well, it's simple. If two things are equal to a third, they must be equal to one another. So equate these two things. And honestly, that's it. Negative delta U is equal to delta K. This is actually the first, this, this alone is equation is conservation of mechanical energy. But it's not very practical. Of mechanical energy. So we can manipulate it a little bit to get a different form of that we'll use more regularly. Let me manipulate a little bit. The delta quantities then are, well, I'll take the minus u over. So we'll have 0 equals delta k plus delta u. But delta k is equal to k final minus k initial. And of course, this is plus u final minus u initial. So if I get all the initial and final stuff on the same side, wait, am I missing a minus sign? No, no. So this is going to be, so K final, yeah, plus U final, K final, plus U final. And then I have a minus K naught and a minus U naught. So that's the same as minus quantity K naught plus U naught. But I just defined for you a few moments ago mechanical energy. So now I can use that inside. 0. So 0, remember, E is equal to K plus U. So this is initial mechanical energy and this is final mechanical energy. So I can say that 0 equals E final minus E initial. Or um, 0 equals delta E. Or delta E equals 0, let's put it that way. In anticipation of something that I'm going to do. Chapter 8. Delta U or delta E equals 0. This is saying between different positions or different times that the mechanical energy of the system doesn't change. So again, this is another nice form of conservation of mechanical energy. But the form I like the best is just take these two things and put them on different sides. That E initial equals E final. All three of these equations, 22, 28, and 29, are those forms of conservation of energy and mechanical energy. All right. And that's it. Now let me show you how to apply that to problems. I'm going to take equation 29 there and apply it to this guy through a quarter cycle. Going from when it goes back from, when I pull it out to X and let it go, and it goes from X to X naught. I told you it should have a maximum kinetic energy at X naught. So you can figure out what that is in terms of known quantities using equation 29. And so it's a way to figure out velocity without having to calculate acceleration or do a whole lot of work with forces and Newton's laws. And if I apply it, I like to do it. So when you apply conservation of energy, you either need two positions or two times. And so you're not really concerned about what's happening in between those positions or times. You're only really concerned about the influence. That's the nice thing about conservation of energy. Sorry, graduate advisor, graduate research advisor. He's a program director of the National Science Foundation in DC. And he has grants and things for students that you can apply for professors and thinking about doing that, try to find some money for you all, students for graduate research. So there's something that I had posted that I was there's some upcoming grants and money funds. What? Yeah, so 2 points or 2 times. So here, I like to clearly distinguish them. When I start a problem, here we're talking about technique now for applying conservation of energy. So in this problem, I will call this like position 1, and then this position 2 as the thing is moving back, just to clearly establish that. So that when I apply my energy thing, I'm going to label it like that. So I start off, and again, of these 3 versions, this is the one that I use as the practical version for problem solving that I like to start with. So if I want to know apply. So the problem is apply conservation of energy to determine the velocity of the object as it goes through the equilibrium position, starting from rest at position X. So apply conservation of energy to find V speed, basically V naught or V, I guess I call it V2. V2. Starting from rest at position 1. So we just say that the total mechanical energy at position 1 has got to equal the total mechanical energy at position 2. The definition of mechanical energy is kinetic plus potential, so K1 plus U1 has got to equal K2 plus U2. Evaluate the zeros before you start. There's some things that are going to be zero. If I'm starting from rest, that means, well, I didn't kind of put down the information, but what's known, let's do it here. We know the mass of the system. We know basically delta X. So we know X, naught and X. And that's it, right? Explicitly. But implicitly, we know that V naught is 0 because it starts from rest. And we know that basically U naught, well, I don't want to confuse these. I'll call it V1 is 0. V1 is equal to 0. And U2 is equal to 0 because delta X is 0 at that point. That's implied. So definitely want to look at the information given before when you're applying conservation of energy. But that said, going back to equation 30 here, I have some zeros that I can evaluate based on that implicit and explicit information. That guy is 0 because U2 is 0, right? Delta X is 0 there. And K1 is 0 because V1 is 0. I guess I could have put in the values. Actually, U2 is not, that's not a delta X. I said delta X is 0. That's not X at a position. So the potential at that point is 0 because it's defined to be 0 at that point because of how we set up the coordinate system. Okay, so that said, go ahead and put in the formulae for the for these things. So what I will then have is actually, let me make this 30. This guy 31. So that the potential energy, 1/2 m x1 squared equals kinetic energy, which is always 1/2 mv squared, but that's mv2 squared. But look at that. That's only one equation and one unknown now, because the unknown is this guy. Because x1 is the thing, I know that. So solving then for v, I get, so we see a lot of things count. We see that 1/2 cancels out, the mass cancels out. No, sorry, it's not 1/2 mv squared, it's 1/2 k. It's not 1/2 mx squared, it's 1/2 kx squared. Sorry about that. 1/2 k. Yes. That's the potential energy function for a spring. So the masses don't cancel out because that would make sense. So we get, solving for V2, we get that V2 is equal to x1 squared times k over m. Let's write it like this. K over m x1 squared, and all of that to the square root. Okay. And the nice thing about that is that you can do that without having to evaluate the forces. We didn't say anything about the Hooke's law force or anything. It's implicit in the potential there. And so, it can be a nice alternative, at least for finding velocity to determine. We don't need to find the acceleration first. In fact, we could go back and find the average acceleration now that we have this velocity, the final velocity, assuming that the initial velocity is 0, by using the equations of motion. What you think about that? Any questions about that? We're at the break, but I'm going to go ahead and do another one real quick. This is going to be fast. And that's this guy to show you. And then when we come back after break, we'll put it on the plane. This guy. I picked it up, dropped it. Again, dropping it from height h at initial velocity 0. How fast is it moving just before it hits the ground? We've done that probably before, okay, but I'm going to do it using conservation of energy. So hopefully I won't have to write it up. Get that. So yeah, just do it right here. And you can compare it back to the answers we got previously when we did that using kinematics and the equations of motion. But yeah, you pick an object up, so height h above the ground. M is here. Find a coordinate system, right? X, Y. This is position Y equals H. Let's call that Y naught in this Y equals 0. So the object is going to, initial velocity is equal to 0. It's going to drop down. And you want to know the final velocity. That's basically the problem we did on the first day. Now we had to use equations of motion to do it in here. All I need is, if I use conservation of energy, 2 positions. Initial position, final position. Apply conservation of energy. Again, 1, 2, 3, 4. The total mechanical energy at position 1 equals the total mechanical energy at position 2. At the top, we've got kinetic plus 1 plus potential 1 equals kinetic 2 plus potential 2. If the initial velocity is 0, then K1 is 0. And if I set up my system so that the origin is here, when you get down, then the 1/2 kx, x2 is equal to 0. So that guy is 0. So again, what we have is the potential energy at position 1 equals the kinetic energy at position 2. And as I described before, what's really happening is gravity is doing work on the object and is converting the potential energy at 1 to kinetic energy at 2. So 1/2 K1 squared equals 1/2 M 2 squared. Yeah, and so basically it's this. Well, I do a y since we're like this. Give some variation. So yeah, you just solve for v and you have the same general formula. That v2 is equal to the square root of y1 squared over m. Wait a minute, what? There's no spring in that. Dude, I think I need to take a break. Sorry. Duh. Sorry. I'm so sorry. I need to take a break. The potential energy for this is not 1/2 kx squared, it's mgh. Duh. Right? Gravitational force down, the force on this is mg. Right? So the potential energy function we derived for gravity is mgh or mgy. Sorry. So in this case, the m's would cancel, but then I still solve for v, and I get that v2 squared, or v2 is equal to, so yeah, it's just going to be the square root of 2g or y1 or 2gh. And that is consistent with solutions we got before, but when we just used conservation of energy, or when we just used kinematics. Sorry about that. Ooh. So much of these types of problems, they're in chapter 8. So this is like halfway. Basically, at this point, we've done almost half of chapter 8 as well. I'm going to go to break right now, but I want it to be a working break, man, because I got to take a little bit longer break, I think. But also because I want you to this to sink in, and we're going to apply this now to a plane. We'll do the frictionless plane first, and then we'll do friction. So I'm going to set those problems up for you before we go on break, so we can work a little bit longer over the break. This is actually kind of fun. This came pretty naturally for me, you know. Hopefully I've laid it out for you in such a way that it's pretty easy to understand and reinforced by your reading in the chapter. So the first problem we'll do is block on a plane, but with frictionless. We'll do this guy. And it's just simple. You got a block here at the top, M1. And let's say that we have an angle theta. And let's say I got to give you another parameter. Let's say that we know the height h right here. And the initial velocity is 0. So use conservation of energy to determine what the speed of the block is when it gets down at the bottom of the ramp. So use conservation of energy to, and I'll call this position 1, position 2. So use conservation of energy to find V2. Okay. And we're going to assume so mu equals 0. So do it for that guy. Then do it for this guy. Again, frictionless. Got block 1 here, but in tandem with block 2. Yeah, in tandem with block 2. And again, mu naught equals 0. And assume the only thing that's given is M1, M2, theta, and H. And if you're on a roll, then go back and do those same 2 problems, assuming there's friction. That's 4 problems. Probably won't get that far, but just at least try to do this one, and maybe you can get that one done too. I'm going to give you a hint, especially on this guy. Something that threw me off quite a bit when I was back in the day. Another thing I didn't stress when I was doing these examples, because it's not obvious, but it's going to become obvious with this problem. You don't have, when you're using conservation of energy, another reason that is very simple, it's much simpler than Newton's laws, is because energy is a scalar quantity. So you don't have to worry about any vector stuff. And that's nice because one of the issues that we had, one of the ongoing discussions that we still have, is this idea when you're dealing with this problem of how to deal with the fact that they really look like they're going in what we conventionally would call two different directions. And by the way, I thought of another way to justify the thing I'm saying is that when we describe one direction up and one direction horizontal, the universe doesn't know anything about that, right? Like even that. Like we assume that that's an absolute truth because it just seems logical and makes sense mathematically and it gives us right answers. But that's just one variation. Like it doesn't, we could have set up a situation so that, and we don't, but we could set up so that that's one direction, like going down and then turning. I know that doesn't seem reasonable because it's not really logical in the way that we think, but mathematically speaking, you could define it as that, and then everything has to adjust to that. So the fact that we say one direction is up and the other direction, like that's because we have a Cartesian coordinate system where we talk about the orthogonality between the directions. That's a definition, it's the way we define it. But it doesn't have to be defined that way. We can define it any way we want. So, and yeah, it might be illogical and have problems. Sure, okay, fine. But I'm just saying that we could do it if we wanted to, and if we define it that way, then that's what it is. And there's nothing wrong with that from a purely mathematical point of view, maybe from a sensible or logical or whatever. But yeah, and so here, the idea that when I kind of do that here, I say we're starting over this direction and I just, allow the coordinate system to transform over the thing, that's fine. I can do that. I can do that. But the point I was making is that we have to spend time justifying it because we have to account for those directions in some way. Have to have some sort of transformative equation to make sure that one coordinate system is related to the other coordinate system. And for me, that's just a kind of an easy way of having to, it's basically a shortcut from having to have two different coordinate systems and then having to have a transformation relationship between them. It's just basically that's what I'm doing. But it's it's just a shortcut to that. But we don't have to worry about that with energy because energy is a scalar quantity. So we just add, if we can figure out what the potential energy is here, what the potential energy is here, then we just add them. And it's relative to, some coordinate system that we want. We don't really even have to define them relative to the same coordinate system. We actually don't. I can define this one guy relative to the ground. And if it moves through a height 8, but I got to be careful because, yeah. Well, actually, I guess. If I have to find this relative to 8, yeah, because it's still, because even it's moving along the plane there, so I have to define it in terms of that tower. Yeah, I think that, but it's rather, does this energy increase or decrease? Well, if I'm defining it relative to this point, then yeah, it's going to have to be a negative because that's a negative h that it goes down once it moves through that distance. And does it increase the overall energy or decrease? It should increase it. So I'd have to make sure that adds in would be negative. So I'll take it on the other side. It's going to be positive. That's right. Mhm. So that loses potential energy. But this also has to lose potential energy relative to this point. And it will if it's moving through a negative distance going down. So it's negative and negative. the delta here is negative. That's negative number. Well, actually positive, sorry, because that's negative in this. So I'm just thinking in my head, it's actually some minus signs in it, but just take that into consideration. We'll do that, see what we get. Okay. All right, so let's go ahead and break right now. And so the next guy, well, you've got two different objects. So I'm going to label three different positions. Now, position 2, what you can do is do kind of a translation here, like kind of, it's like basically, you do one of two things. I can put this at position 1 and 2, and then I can put this one at position 3 and 4. But since position 3 is just some constant distance of position 2, I could make that constant 0. In other words, I could shorten this string so that it's right at that position as well. So what I'm going to do is kind of do that, right? I'm going to say like there's a position 2 here, but the final position of block 1 is the initial position of block 2, and that's like maybe that point right there, just to make it simpler. So, and that position is the 0 potential energy point, essentially for both, actually. So, E1 equals E2. Now I've got 4 terms as opposed to 2 on each side. I've got, yeah, I guess I should make it, I gotta make another distinction now, and I've gotta change my number. I'm gonna make, oh no, that was 1 and 2. I wanna make this block A and this block B. Or, yeah, let's just do that. So I've got the kinetic energy of block A at position 1 plus the potential energy of block A at position 1. And I've got the kinetic energy of block B at position 2, and the potential energy of block B at position 2. And that equals the kinetic energy of block A at position 2, and plus the potential energy of block A at position 2, plus the kinetic energy of block B at position, to make it 4 or 3, so it doesn't be confusing. Position 3 plus the potential energy of block B at position 3. Now let's do the zeros. Kinetic energy here for block A, and at position 2 for block B are 0. So A1 goes out at 0 kinetic energy, and B2 kinetic energy 0. Now the potential energy is also 0 here for this guy. And then the potential energy for block 1 is 0, or block A, excuse me, is 0 here. And both of them have kinetic energy when they fall through their distance. And it's the same distance. Now the kinetic energy, the speed will be the same, but the kinetic energy won't necessarily be the same because the masses are different. Okay? And that's what I'm saying. You don't really have to worry about any vector analysis or anything, because it's all scalar quantities. Yeah. Now the potential energy that does increase or decrease, so that's a little bit to take care of, and I have done that here. And also that potential energy will be positive, but it's going to be positive in kind of a funky way because it's increasing in a negative direction. So yeah. Anyway, so this is going to be one mg. Basically, I could say h, but I'm going to say um, well, yeah, sure. It's and we know that h is going to be delta x sine theta. So I'll go ahead and put h there. Sure, why not? H. And it is decreasing. So because final minus initial would be a negative, if I'm thinking of it that way. So yeah, so it's going down. So that would be a negative h. Well, actually, that's over here. So yeah, that's this guy. So mg, um, negative h, and then yeah, that's the only thing I have on that side. And then over on this side, 9, 10, 11. Kinetic energy is always 1/2 mv squared. So 1/2 m a v2 squared, and then plus 1/2 m b v3 squared. And then this guy is going to be, again, it's going to be mg. But obviously, if this distance falls through a vertical distance of h, which it does, this also has to fall through a vertical distance of h magnitude because they're connected. But if I'm saying this is 0, then final minus initial is a minus h minus 0. So that's also a minus h, I guess. I said it's plus, but the point is it has to have the same sign as this guy. They have these changes in potential energy have to have the same sign. It doesn't make sense that this would lose energy and this would gain energy, or this would gain energy and this would lose energy. It makes more sense that if this loses energy, this loses energy. Or if this one gains energy, this one gains energy. So that's the point that I'm trying to point out here. So that's also a negative h. Um, I see a potential problem there because have I defined it? It's final minus initial. Well, they're not the same m, so maybe it'll work out. But I think is that this is MA and this is MB. I'll see in the end. I'll see in the end. I'll see in the end. So we get and the other thing is we have to say that the speeds are the same. So V2 equals V3, just equals V. So I'm gonna bring this guy on over on the other side here. So I'm gonna have M A G M sub A G minus H, and then plus M sub B G H. And then this guy is going to be 1/2 M A V squared plus 1/2 M V and B V squared. Okay. Um, Factoring out in a GH, I'm going to get 12, 14. So GH, this is going to be MB minus MA. Switching around, and over here factoring out, I get 1/2 b squared, and then ma plus mb. Looking pretty good. Yeah, I think this is right. This is right. The minus sign should be there because that's what we got when we got. You're going to see a term very similar to what we got when we got did it with the force laws. So coming up here, we are going to have the plus over here. So now then the V 15 V is going to be equal to, so if I take the 2 over on the other side, and if I still have V is equal to 2 GH MB minus MA over MB or MA plus MB, and then the square root of that. Now, this is a little bit counterintuitive to me. I would have thought that they would have added. I know I just said that we should get, but still, because if there's friction, you subtract. But I think the best way to check this is to do it with force laws and see if I get the same answer. Now, that'll be a good check for you. Now, you remember that what we said is with force laws. So let me box this in. And let me remind you of how we did this problem with force. With force, free body diagram. All right, we've got normal force up the plane. We've got mg cos theta down the plane, down the, up the, not up the plane, but up the, perpendicular to the plane, and mg cosine theta perpendicular in the opposite direction. But down the plane, we've got mg sine theta. That's the other thing. Because we're going to have to put that in too. Yeah. So let's go ahead. It would be in here. It would be in the h. So if I put in the fact that h is equal to delta x sine theta, we said over here, right? Sine theta is opposite delta x over sine theta is opposite h over. So h is equal to delta x sine theta. So this would actually be v is equal to 2g delta x sine theta ma minus m. V is equal to 2g delta x sine theta quantity mb minus m. In fact, let's just keep that as a kind of a factor here. Delta ma plus mb. And then all of that to the square root. All right, so with force laws, mg cos theta, normal force, and mg sine theta. And starting off, down the plane, we just have mg. It's going to, down the plane is it's Newton's second law. Net force equals m and we've got two objects too. So the one here we actually did that problem. I don't remember the answer about it. I'm confused on the minus sign. Well, we have to do it all the way. So okay, have to do it. So for block 1, I've got n. Well, I won't need that one. I won't need the vertical direction, so I'm not having friction. But down the plane, I also have tension. So basically, T plus MA G sine theta equals MAA. And for this guy, it's going to be, for block 2, we'll have, we'll keep the numbering going, 17, 18. So I'm going to have mg down the plane minus t is equal to, and that's b, mba. Eliminating the tension, oh, this was an a. Okay, maybe that. Maybe. Yes, because that's the minus sign. So when you add the equations, you're going to have mbg minus mag sine theta equals ma. Or ma a plus mba. Well, I'm getting the minus sign there, but there's another issue that's popping up, and that's this sine theta is not on both. So when I factor out, that's acceleration. So I need to use that. Keep that there. Okay. So clean this up. I'm going to have MB. In fact, I'm going to factor out a G from both of these, like I used to do. G, that will be MB minus MA sine theta. And then equals A times M, A plus M, MB. So that A is equal to G times MB minus MA sine theta over MA plus MB. So that minus sign is there, but the problem is the sine theta is multiplied by both, and either I made a mistake somewhere or it's not quite the same, but because the delta x is there also, so we have to keep going. So, but that's the acceleration, this is a velocity, so not quite the same things. But now that I have the acceleration, I need to get the velocity. And the velocity is, I can use either one, right? Like either object. And, well, that's where it's going to probably work out. I'm going to use B, and I'm going to use equation of motion. So V squared equals V naught squared plus 2A delta X. That's probably what's going to come in. So V naught squared is 0. So V squared, 23, is going to be equal to the square root of 2A, so 2 times this thing, so 2, that's times it. So 2 times all of that, so it's going to be 2 times G G and B minus MA sine theta over MA plus MB, and then times delta X. All to the square root. So that becomes V is equal to, let's multiply that out, you're going to have 2G delta X. And the only problem is MB minus MA sine theta over MA plus MB. The 1/2. So almost the same, except that the sine theta I have here is out of the integral, and that was on the inside. So the minus sign is fine. So somehow I Can it be the same though? That's going definitely false to H. Let's go ahead. H is H. And why do I have to do this square? Hmm. What type of formula? Oh, because that's not the same X. This is H. This is H. And then you're going to have a squared inside there. Yeah, there's something going on with the signs with this, doing it two ways, but it might be how I define the position here. Might be. I have to think about that. More of a mathematical definition in physics, but still, it's just a slight constant multiple off, but I can fix it. I have to think about that. I have to redo it in order to get the thing. But what about if I found the velocity with that using that equation? I said, oh, I gotta be careful. I gotta be careful because when I did that, that's based on a different coordinate system. It's based on the coordinate system at an angle. Yeah, it's scalar, so does that still matter? Hmm. Hmm. Out here, I would still have h becomes delta x sine theta. Still not quite right. Is that G delta x sine theta? So this term I would have sine theta squared. And here I still have just sine theta. So I think that's a matter of, yeah, I think maybe the coordinates defined differently because when I get this acceleration is at an angle. The acceleration is theta would be, yeah, that's theta, this theta. So this would be sine theta. That would be sine theta. So I do the sum of the forces. And she would just be straight down. Now I have a component of the normal force. numerical formula here. Attention to, yeah, it becomes more complex. Yeah, I think it's just a matter of coordinate system. I have to think about that one. I think it's I'd mixed coordinate yeah, mixed coordinates, coordinate axes, and I thought it didn't matter because energy is a scalar, but there may be some geometric considerations that I'm not thinking about. Because that's what's happening here. It's off by a sign, a factor of sine of theta on one of the terms, and I think it might have to do with that. I don't think I've ever actually done this problem before like this, which is why I'm not knocking it out. I've only done it with um, with force laws. So I think there's some subtlety here that I need to consider regarding the axes. Well, I'm going to, I got 10 minutes, and we can work on that at least for the next 10 minutes, see if I can square that up. Try something different. Going back here and doing what I don't normally do, which is to choose the axis so that it is, we have to have components of acceleration. If I do that, then we've got normal force here, got mg down, got the tension force here. Okay. So now I'll have, and is this theta? So let's see, I have to work that out again. This is theta. But do it like theta, 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 theta. This is theta. This is theta. And so in this case, um, I have accelerations in both directions. So vertically, I'll have y direction. I'll have n cosine of theta minus mg equals m. Acceleration, this acceleration is down the plane, and theta would be, okay, so that's theta, yes, so that would be cosine mg cosine of theta, or a cosine of theta. So m a cosine of theta. And so for the x direction, it's just going to be t equals m a sine of theta. And from Yeah. Oh, and it also has the x component here also. So, so n sine of theta plus t equals n. Theta. We've got three unknowns. Over on the other side, basically for the other block, this is block one. Block two, I have A, the, the, the block two is going to be gravity minus, so and B, G minus T is equal to, that's the x direction, so that's going to be M B times A sine, right? The Y is on there. And so then this is, yes, I'm going to add those two equations. If I add those two, that eliminates T. Work out T plus theta is equal to A times. Let's keep it like this. Plus sine theta. Now I have to substitute solve that for here and substitute in. Or I could go back and solve that for A and substitute in. I do it in my head. Yeah, it's a mess. It's supposed to be. So I should ask the way to go back to the problem. That's a really cool by it. Yeah, I do it up, but it's not going to be in the same form. I think something is, I missed something a while back. Do it over. I'll let you go. It's 4:30. Um, I'm gonna work this out and maybe talk about it next on Wednesday or either post it. Um, Work out the solution for this guy. Mhm. Mhm. Yeah. Mhm. 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 For the kinetic energy. Mhm. 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 Squared. Squared. And the potential of the system is just going to be if these are both negative, right? Mhm. Mhm. Negative h. Just because it loses, this is final minus h minus 0. And this is 0 minus h. But this is the potential of the air. But where did that sign come from? So then this is just going to be in you know, G H and B minus a 1. This would be 1/2 B squared over plus MB, so that B squared is equal to 2GH and B minus MA over, that's the same right there. And so where that becomes 2G Okay, so conservation of energy, definitely use that twice. So I have to go back and look at the force thing. Make that work out. I think there's some issue there with that, turning that angle, and basically turning it the angle theta. Yeah. So, all right. Work on that. There's something. Oh, is anybody still there? Aaliyah, Armand, Arcady, are you there? Okay. Well, I guess not. I'm going to I'll work this out and we'll talk about it on Wednesday, this specific problem. But ultimately, we're almost finished with chapter 8. The last thing you have to do is something called a modified work energy theorem and show how to handle friction with kinetic energy. And those last two problems, we can go back and do those. Use the modified work energy theorem to use those with friction. So, yeah. All right. Well, class is missed, and I'll see you on Wednesday.